Hi everybody, welcome to this second part of the lecture on deduction, which covers section 2.5 in the Page and Gamboa or P&G text. And we're just taking a look at some additional work as it pertains to the writing of deductive proofs. And there's some interesting variations on some of the proofs we've already examined. And we're just kind of taking things a bit further with the realization that we can use formulas that we derive as the basis for other proofs. So what does a proof afford? If we're given a proof, it is a straightforward to extract the theorem it proves, and we're working again with this turnstile symbol, which sort of just looks like a T-square, sort of pointing to the right. And on the left of the turnstile, we put all of the different formulas annotated as assumptions in the proof, except for those that are discharged. And this is something that is introduced to address the possibility that some of the assumptions can't really be assumed outside the context of the proof itself. So when we discharge an assumption or a hypothesis, we're essentially saying that we're no longer making the assumption that the hypothesis is true. However, we usually discharge an assumption after we've proven what we sought to prove. And so after the turnstile, we write the formula in the conclusion at the end of the proof. And you can see that here as we look ahead a bit, that what ends up on the left of the turnstile, which again is this kind of like T-square looking symbol pointing to the right, we have our hypothesis, and at the right of the turnstile we have our conclusions. And typically what occurs after the turnstile is the proof, or I should say the formula that we sought to prove. What does it mean to say an assumption is discharged? In theorems, assumptions appear to the left of the turnstile. And here is the turnstile symbol right here. And what we're calling an assumption is essentially a hypothesis. And in theorems, a discharged assumption is not counted as a hypothesis. One reason for discharging an assumption occurs in the proof of implication, which is represented by this rightward pointing arrow. And implication does not place any constraints on the value of its left-hand operand. And what that means is that when we write the proof for implication, we're explicitly discharging the assumption we made to assert the truth value of the left-hand operand of the implication operator. And here we have a theorem which is self-implication, and we're proving that A implies A. And this particular theorem has no hypothesis. And the reason why is because the only hypothesis we have is that we're assuming A. And you can see the last step in the proof is that we discharge A. So we can't use this as the basis for a proof that requires assuming A. You can see the discharge of A occurs after we've proven what we sought to prove, that A implies A. And you can see that there are really only two possibilities here. Either A is going to be true or A is going to be false. And as we know, true implies true and false also implies false. So you can see the truth of this hypothesis by just making a very simple observation. And it does require understanding the way implication works, which has a truth table. And with knowledge of the truth table for implication, we can safely assert that this particular theorem does in fact prove that A implies A. And here we have a theorem which is the logical OR commutes, or A logical OR B implies B logical OR A. And you can see up the top here, we again have our logical OR, which is this V-shaped symbol. We also have our turnstile, which is this T-square pointing to the right. And we start in the left column here. There are actually two columns in this slide, and we're starting at the top of the left column. We're assuming A logical OR B is true, and we're assuming A is true, and then by logical OR introduction 2, we can state that B logical OR A is true. And then we're using the implication and introduction theorem to show that A implies B logical OR A. We're discharging A, which is a requirement of the implication introduction theorem. Then we're right up here at the top of the column at the right, and we're assuming B, and we're utilizing logical OR introduction 1 to state that B logical OR A is true. And then we're using implication introduction to state that B implies B logical OR A. We're discharging B, which again is a requirement of the implication introduction theorem. And then we are utilizing logical OR elimination to show that B logical OR A is true. And you can see this is what we sought out to prove. This is a fairly sophisticated proof. There are several steps. And with a little work, it isn't difficult to see why this proof is valid. So some more on proofs and theorems. Deductive proof is one-directional. Most of the theorems we have proved so far using natural deduction turn out to be bidirectional. And the proofs we have encountered so far only go in one direction. The theorems we have encountered so far are provable in both directions. And here we have the implication chain rule, in which if we can state A implies B and B implies C, that we can prove A implies C. So we start at the top of the left column here at the left, and we make the assumption of A. We make the assumption of A implies B, and then utilizing the modus ponens theorem, we can state that B is true. And then we can assume B implies C, and we can apply modus ponens to show that C is true. And then we can use introduction to show that A implies C. And then we carefully discharge A. And so we've shown in this proof that if A implies B and B implies C, that A also implies C. And here we have modus tollens, which states if we can assume as true that A implies B, and that not B is also true, that this shows that not A is true. So at the start, here at the left, we assume A implies B. Then we make the assumption that not B is true, which would seem to indicate that B is false. And then by not elimination, we can show that B implies false. And then using the implication chain rule, we can show that A implies false. And then using not introduction, we can show that not A is true. And here we have the theorem, which is not forward, in which we can show that if not A is true, this implies A is true. And you can sort of just look at this and realize that what we're saying is that we're essentially negating a negation. And if A is true, negating A results in false. And then if we negate that again, if we negate false, we get true. And so just by some simple sort of like casual reflection, you can see that this theorem holds water. So we're assuming not A is true, and then using not elimination, we're making the hypothesis that not A implies false. And the only time implication with a false at the rights as the right-hand operand results in true is when the left-hand operand is false, and that'll be precisely when A is true. And this is, we're using the reductio ad absurdum theorem to show that A is evinced by not A. So we're starting with not A, and then by applying a couple theorems, we're demonstrating that A is true.